Good morning, good afternoon, good evening, wherever you are. I hope you are enjoying the IEEE Education Week that we are in the midst of. And this session is composed of a webinar presentation by me on a topic that hopefully is on everybody's mind, AI in higher education. But before we get started, it is my pleasure to introduce Dr. Arnold Pears, the president of the IEEE Education Society, for his opening remarks. Arnold, the floor is yours.
Thank you very much, Babak, and welcome everybody to what I hope will be, well, what I know actually, based on my past experience with Babak, will be an incredibly uh, exciting and forward-looking webinar. So uh, just as a way of introducing today's presentation, as we've all been, I think, struggling with AI. I myself was in Portugal just last week discussing with the Minister of Education and the Vice Presidents for Education of the different Portuguese universities. The big challenge that derives from probably the one most serious thing that AI disrupts in our educational environments, that we can no longer use product as a proxy for process, that it's impossible to link the output of a student activity back to the process, because AI can produce a lot of that product for the student without them necessarily engaging with any of the activities or intellectual or cognitive development processes that we have historically been able to link to those outcomes. And I think that's probably, from my perspective, the greatest challenge that we face, that one of our fundamental methods of assessment has, for the first time in probably human history, been completely undermined by new tool and technology. And I'm quite sure that Babak will probably bring this up in his talk, because I think it is a question that faces all of us. As president of the society, however, I'd like to just take a couple of minutes to thank you all for being here. The Education Society is a cross-cutting society of the IEEE. We are a society that I think has a relevance to every other IEEE society, in the sense that we contribute to the educational mission of engineering. And our goal is to help all engineering educators worldwide to progress their engineering education and to gain new insights, new ways of facilitating learning for the most important stakeholder group we have, our students, who are the future of the planet. And of course, we have an extensive collaboration with other aspects of the IEEE, the Education Activities Board, and the Faculty Resources Committees, and other aspects of the IEEE organisation. And I see some names here in the list of attendees that I recognise from those contexts as well. So welcome, Raphael, for instance. So without further ado, I think let me pass over the floor completely to you, Babak, and I really look forward to listening to your words of wisdom in this regard. And I also want to thank you personally for taking the time out of your busy schedule to contribute to the society and to our audience here today. So welcome, everybody, and let's look forward to 50 minutes of stimulating presentation and discussion. Thank you.
Appreciate it. Thank you, Arnold. And welcome, everyone. I'm going to share my screen. And again, since this webinar was scheduled to be 1 hour, I've been fairly ambitious in preparation of my remarks. We may not have opportunity for Q&A, but I'm hoping that I will be able to address as much as possible in terms of relevant to strategic topics, and definitely, some of the topics that or issues that Arnold brought up will be hopefully addressed. So let us start with sharing the screen. And hopefully everybody can see the first slide. So thank you for being here. It is a pleasure to join you for this discussion on one of the most important issues facing higher education and the engineering profession today. How we prepare students for a world increasingly shaped by artificial intelligence. My talk today is titled IEEE's Role in Shaping AI-Ready Engineering Education Globally, and I want to frame this not simply as a technology discussion, but as a strategic educational imperative. This presentation is intended for faculty, academic leaders, and professional volunteers who recognize that AI is not a passing trend. It is becoming a foundational capability that is reshaping engineering practice, workforce expectations, instructional models, and institutional competitiveness. My goal today is to make the case that we need not only incremental changes, but a coordinated, thoughtful transformation of engineering education. Before I begin, let me briefly situate my perspective. My work sits at the intersection of engineering education, institutional leadership, and the global professional community through IEEE. That vantage point has made one thing very clear to me. The changes we are discussing today are not isolated to one country, one discipline, or one sector. They are global, cross-disciplinary, and already underway. We are at a critical inflection point. AI is not merely adding a few new tools to the engineering toolbox, it is changing the way engineering problems are framed, analyzed, solved, and communicated. This is important because engineering education has traditionally been built around durable fundamentals, long established methods, and carefully sequenced curricula. Those foundations still matter. But now, on top of those foundations, AI is transforming workflows, design processes, decision making, simulation, communication, and even creativity. This means that the central question before us is no longer whether AI matters for engineering education. That question has already been answered. The real question is whether our educational systems are adapting at a pace and depth that matches what students will face when they graduate. In many cases, the answer is not yet. And that is why this moment is so consequential. We are not simply updating a curriculum. We are redefining what it means to educate an engineer for the next decade. AI is transforming every engineering discipline. And that point is worth emphasizing because sometimes AI is still perceived as something primarily relevant to computer science. That is no longer the case. In civil engineering, for example, AI is increasingly being used for structural health monitoring, predictive maintenance, and smart infrastructure management. Systems can analyze data from sensors embedded in bridges, roads, and buildings, detecting emerging weaknesses and support earlier intervention. This has enormous implication for safety, cost, and public infrastructure planning. In mechanical engineering, AI is reshaping design and manufacturing. Generative design tools can explore thousands of possible design alternatives based on performance constraints, materials, and manufacturing conditions. Engineers are no longer limited to what they can manually iterate. AI can surface novel configurations that are lighter, more efficient, or more sustainable than conventional designs. The same pattern continues across electrical engineering, computer engineering, software engineering, and biomedical engineering. In electrical and computer engineering, AI is increasingly used in chip design, system optimization, embedded intelligence, and edge computing. Engineers are now designing systems that are not only process signals or execute control logic, but also learn, adapt, and infer in real time. That fundamentally changes both technical design and system architecture. In software engineering and computer science, the shift is even more visible. Developers are now working with AI assisted coding tools, large language models, intelligent agents, and automated software generation. This changes what it means to be proficient. Increasingly, engineers need to know how to supervise AI-generated code, validate outputs, and architect systems that incorporate AI components responsibly. In biomedical engineering, AI is driving progress in imaging, diagnostics, signal interpretation, and personalized treatment planning. Across all of these fields, the pattern is unmistakable. AI is not replacing engineering disciplines, it is redefining how engineering is practiced within them. Despite these developments, many academic programs are evolving too slowly. One of the most visible gaps is structural. AI is often still treated as a specialized elective rather than an integrated fundamental capability. Students may have the option to take one machine learning course or one AI elective, but that is not the same as learning how AI is transforming their own discipline. A civil engineering student, for example, may graduate having never seen how AI is being used in infrastructure analytics. A mechanical engineering student may learn classical controls and design, but not how AI informs robotics or predictive maintenance. Another major gap is practical experience. Many students are not getting enough exposure to real data sets, industry standard tools, cloud platforms, computing resources, or production scale AI systems. They may learn definitions and algorithms, but not how AI is deployed, evaluated, and governed in real applications. That matters because employers increasingly expect graduates not just to understand concepts, but to work fluently with modern tools and workflows. There is also a deeper curricular problem, which is fragmentation. AI is inherently interdisciplinary. It intersects with ethics, data, systems, design, domain knowledge, and communication. Yet our academic structures often remain siloed. Programs are organized by department, courses by traditional categories, and faculty incentives by narrower expertise. As a result, students may learn pieces of what they need, but not how to connect them. We also need to acknowledge the challenge faculty face. The pace of AI development is so rapid that it can outstrip normal faculty retraining cycles. Many institutions have not yet created the time, incentives, or support needed for meaningful curriculum redesign. So it is not simply a matter of faculty willingness. It is also an institutional design question. If we continue with outdated course structures, insufficient hands-on exposure, and compartmentalized thinking, we will continue preparing students for yesterday's jobs in a world already shaped by AI. This curricular lag is especially concerning because the global competition for AI-ready talent is accelerating. Governments around the world understand that AI capacity is tied to economic competitiveness, national security, innovation leadership, and workforce development. That is why we see substantial investments from the United States, China, the European Union, and many other regions into AI research, AI infrastructure, semiconductor ecosystems, and talent pipelines. Industry, meanwhile, is moving aggressively as well. Employers are looking not only for AI specialists, but for graduates across engineering disciplines who can work effectively in AI-augmented environments. Companies increasingly expect new hires to understand data-driven flows, automated systems, AI-assisted design, and the limitations of AI tools. Even when the role is not explicitly titled AI engineer, the expectation of AI fluency is rising. This has direct implications for higher education. Institutions are no longer competing only on traditional academic reputation or geographic location. They are increasingly competing on whether they can produce adaptable AI-ready graduates who can create value in a fast-changing environment. We already see universities around the world launching AI institutes, interdisciplinary centers, AI-focused degrees, and industry partnerships to strengthen this position. The broader point is that talent development has become strategic. The institutions that move fast and move thoughtfully will be the ones that lead. Those that move too slowly risk losing students, employer relevance, and influence. So when we talk about AI readiness, we are not only talking about curriculum quality, we are talking about institutional competitiveness, national capacity, and global leadership. So far, I have focused on how AI is changing engineering practice and workforce demands. Now I want to build a shift to a second major dimension of the transformation. How AI is changing teaching and learning itself. This is equally important because AI is not only something we must teach about, it is also something that is changing the educational process directly. Students are already using AI tools to learn, solve problems, generate content, explain concepts, debug code, and prepare assignments. Faculty are increasingly exploring AI for feedback, content generation, tutoring, and assessment. That means the classroom is changing whether institutions have fully planned for it or not. Our responsibility is to shape that change intentionally so that AI enhances learning rather than weakening rigor or critical thinking. Generative AI is fundamentally reshaping how students learn programming and how engineers develop software. One of the most immediate impact is on coding. Students can now receive real-time help generating code, completing functions, debugging errors, and understanding syntax. This can be extremely powerful because it reduces time spent on routine struggles and allows students to focus more on logic, design, and problem solving. At the same time, generative AI is changing explanation itself. Students can ask for concepts to be explained at different levels, in different formats, and from different angles. A student can request a step-by-step explanation, a simpler version, a more technical version, or a comparison across approaches. That kind of on-demand explanatory support was not previously available at scale. When used well, it can improve access, confidence, and persistency, especially for students who hesitate to ask questions in class. There are additional benefits as well. Generative AI can help with code translation across languages, refactoring for clarity, and rapid prototyping of ideas. This lowers barriers to experimentation. Students and practicing engineers can move faster from concept to implementation, which has real educational and professional value. But we must also recognize the risks. Students may become over-reliant, may accept incorrect outputs uncritically, or may appear competent without deep understanding. That is why the educational goal cannot simply be access to AI. The goal must be disciplined use of AI. We need students who learn how to supervise, validate, question, and improve AI-generated solutions. In other words, the role of the engineer is shifting from being only a producer of code to being a responsible interpreter and validator of AI-supported work. Intelligent tutoring systems are another major area of change. These systems can provide adaptive, individualized learning support at scale. They can adjust the level of difficulty, identify gaps in understanding, and provide immediate formative feedback based on how a student is performing. In principle, this allows for a more personalized educational experience than a one-size-fits-all classroom model. This is especially important in foundational engineering courses, where students often come in come in with very different levels of preparation. Intelligent tutoring systems can help meet students where they are, reinforcing prerequisite knowledge for some while and accelerating others. In large introductory courses, where individualized faculty attention is limited, this can be a significant enhancement. Another important advantage is conversational interaction. Students can engage with AI tools in natural language, asking follow-up questions and probing areas of confusion. This creates opportunities for iterative learning that go beyond static textbooks or fixed problem sets. It can help students understand not just what the answer is, but why. These tools are also promising for online and non-traditional learners who are working full-time, learning remotely, or studying across time zones, may not have easy access to office hours or peer support. Intelligent tutoring systems can extend support beyond the classroom schedule. Done well, they can make high-quality support more accessible and more scalable. Still, we should not be naive about the challenges. Pedagogical quality matters. If a tutoring system gives plausible but incorrect explanations, reinforces misconceptions, or over scaffolds student work, it can undermine learning even while appearing useful. We also must take seriously questions of privacy, data use, transparency, and fairness in these systems. So the promise is real, but so is the responsibility. Intelligent tutoring systems should not replace educators. Rather, they should extend educational capacity while remaining aligned with course objectives, faculty judgment, and sound pedagogy. The long-term opportunity is tremendous. The possibility of democratizing high-quality learning support at global scale. But the implementation must be deliberate. It is also transforming assessment. One of the most immediate applications is automated code grading, where systems can evaluate not only correctness, but also efficiency, style, and performance under different cases. This can dramatically reduce turnaround time and allow students to receive rapid feedback while the learning moment is still active. In addition, AI can assist with feedback on written work, lab reports, technical documentation, and design rationale. This does not mean fully outsourcing judgment, but it does mean that AI can support more timely and more frequent feedback than many faculty can realistically provide at scale on their own. This is particularly relevant in large classes and programs with limited instructional staffing. A particularly important shift here is from episodic assessment to continuous formative assessment. Rather than depending solely on a few high-stakes exams, courses can use more frequent, lower-stakes opportunities for feedback and iteration. AI makes that model more feasible by reducing the operational burden. Students can then learn through repeated practice, adjustment, and reflection. Rubric-based AI evaluation can also help improve consistency across sections and instructors, especially when carefully calibrated. This can be useful in large multi-section courses or in programs seeking more consistent assessment of learning outcomes. But again, consistency does not automatically mean quality. Human oversight remains necessary to ensure that rubrics are interpreted appropriately and that nuance is preserved. The benefits are significant. Reduced grading workload, faster feedback, and more data on where students are struggling. The data can help instructors adjust instruction, identify common misconceptions, and intervene earlier. However, we must be clear about the limitations. AI may struggle to evaluate originality, creativity, open-ended design thinking, and context-specific judgment. It may also introduce bias or false confidence in borderline cases. So the real opportunity is not to turn grading into a fully automated administrative pipeline. The opportunity is to shift faculty effort away from repetitive mechanics and toward higher value educational work, mentoring, deeper feedback, redesigning learning experiences, and helping students develop judgment. At this point in the presentation, it is useful to step back and frame the broader pattern. AI creates real opportunities, personalized learning at scale, faster feedback cycles, expanded access to support, and more adaptive learning environments. These are not trivial gains. They have the potential to improve both learning outcomes and educational equality when implemented well. But AI also introduces real risks: hallucinations, bias, over-reliance, shallow understanding, and the erosion of student agency if tools are used passively. So the educational mission is not to celebrate AI uncritically, nor to reject it reflexively. The mission is to teach students and faculty to engage with AI critically, ethically, and competently. That balance is central to everything else I will discuss. This brings us to the next major theme. What kind of engineer are we now preparing? If AI is becoming pervasive across practice and education, then the profile of the successful engineer must evolve as well. Technical knowledge remains essential, but it is no longer sufficient by itself. Engineers must now work in partnership with intelligent systems, interpret outputs, exercise judgment, and collaborate across boundaries. So the question is not simply how we add AI to the curriculum. The deeper question is how we form graduates who are capable of thriving in an AI-augmented professional environment while retaining. The future engineer will not be defined by the ability to outperform AI at routine tasks. The future engineer will be defined by the ability to augment AI responsibly and effectively. AI brings speed, scale, and pattern recognition. Humans bring context, values, purpose, judgment, creativity, and accountability. The strongest engineering outcomes will come from combining those strengths, not confusing one for the other. This means AI fluency is becoming a baseline skill. Students need to understand that what AI can do, what it cannot do well, and what kinds of errors it makes, how it depends on data, and how outputs should be interpreted in real contexts. This is increasingly as important as digital literacy or computational literacy. It should not be confined to a narrow specialty. At the same time, as AI takes on more routine tasks, the human differentiators become even more important. Critical thinking, creativity, problem framing, ethical reasoning, and the ability to ask better questions all increase in value. Engineers must decide what problem is worth solving, what trade-offs matter, what counts as acceptable risk, and whether a given AI-generated recommendation is actually safe, fair, or appropriate. Human judgment remains essential because AI lacks accountability and cannot bear responsibility. In engineering, that matters deeply. Whether we are talking about a structural recommendation, a medical decision support output, a control system response, or an automated design, a human professional remains responsible for safety, reliability, and ethical conduct. That is why we must educate not only technically capable engineers, but wise and responsible ones. Industry expectations now reflect this shift very clearly. Employers are not simply asking whether graduates know certain equations, programming languages, or software tools. They are increasingly asking whether graduates can function in AI augmented environments, collaborate across disciplines, learn continuously, and evaluate outputs critically. That is an important shift because it means employability is becoming tied not only to static knowledge, but also to adaptability. The graduates who will thrive are those who can combine technical expertise with judgment, communication, and ongoing learning. One major expectation is the ability to interpret it and validate AI outputs. Employers want engineers who do not simply accept a recommendation because it looks polished or plausible. They want graduates who can ask where the output came from, what assumptions were behind it, what the limitations are, whether bias may be present, and how well the output aligns with domain constraints and real-world conditions. This is particularly important in engineering context, where consequences are significant. A design that is optimized mathematically may still be unsafe in practice. A model output may be statistically reasonable, but operationally inappropriate. So interpretation and validation must become core educational outcomes. A second major expectation is cross-disciplinary collaboration. AI-driven work rarely sits neatly inside one discipline. Engineers increasingly need to work with data scientists, software developers, domain experts, business leaders, policy professionals, and users. They need to communicate across technical and non-technical boundaries and help translate domain problem into workable AI enabled solutions. This has strong implications for how we educate students. If we continue to train students only within narrow disciplinary silos, we will not fully prepare them for the collaborative realities of the modern engineering world. Cross-disciplinary teamwork, communication, systems thinking, and project-based learning become more important in this environment. A third expectation is continuous lifelong learning. AI tools, platforms, methods, and best practices are changing too quickly for anyone to assume that formal education alone will be enough for an entire career. Graduates must leave our institutions not only with knowledge, but with the capacity to and disposition to keep learning. And now let us talk about faculty transformation. If students are changing, then faculty roles must change as well. We cannot prepare students for a transformed professional environment using exactly the same educational assumptions, delivery models, and instructional roles we used before. Faculty remains central, but the nature of the centrality is evolving. This should not be understood as eliminating the faculty role or diminishing it. On the contrary, it elevates it. Faculty become even more important as guides, mentors, designers of learning experiences, curators of rigor, and models of professional judgment. Traditionally, faculty were often positioned primarily as content experts and lecturers. That role still matters, but AI is challenging the idea that education is mainly about delivering information. When information and explanations are available on demand, the value of the faculty mentor increasingly lies in helping students make sense out of knowledge, apply it wisely, connect ideas, and develop judgment. So the role is shifting from content delivery to experience design, mentoring, coaching, and higher order intellectual development. Faculty help students ask better questions, tackle ambiguity, synthesize across domains, and navigate ethical tensions. These are precisely the capabilities that become more important in an AI-rich environment. For this shift to happen well, institutions must invest in faculty. We cannot expect meaningful transformation without meaningful support. Faculty need opportunities for AI training, pedagogical development, experimentation, collaboration, and time to redesign courses. Incentives matter as well. If institutions want innovation, they need to reward it. Communities of practice can be particularly useful here. Faculty often learn best from one another through examples, pilots, and shared reflection on what matters. So now let's talk about ethics and responsibility. In the age bias and fairness, any serious discussion of AI in engineering education must include ethics. AI systems raise profound questions about bias, fairness, transparency, explainability, privacy, accountability, and societal impact. These are not side issues. They are integral to responsible engineering. That means ethics must be embedded into engineering education, not added as an afterthought. Students should learn to ask who is affected, whose data is being used, what harms might arise, what assumptions are being built into the systems, and how accountability is maintained. In an age of AI, technical excellence without ethical reflection is incomplete. This is where IEEE has a particularly important role to play. IEEE brings together academia, industry, standards development, professional practice, and a global community of experts. That positioning allows IEEE to support the development of trustworthy AI, educational frameworks, professional development opportunities, and collaborative initiatives that can guide institutions through this transformation. IEEE is valuable not only because of standards, though those matter greatly, but also because it offers a platform for shared learning and collective leadership. It is a rapidly changing in a rapidly changing environment, institutions benefit from being connected to a broader community that is working on the same challenges from multiple perspectives. I also want to specifically encourage engagement with the IEEE Education Society initiatives, including the IEEE Educational Society Days. You see the date and the link on the slide, and I will share the slides with you so you have that information handy. Events like this create opportunities for educators, researchers, and leaders from around the world to exchange ideas, examine emerging practices, and build a collective vision for the future of education, engineering education. What is especially important about these forums is that they are not limited to one institution's local concerns. They allow us to situate our work within a global conversation, which is essential because the AI transformation is global in scope. We all have something to contribute, and we all have something to learn. Having discussed the present moment, I want to conclude by looking ahead. What might the engineering classroom of 2030 look like if we respond well to this transformation? I believe it will be more personalized, more connected, more adaptive, and more continuous in how learning is assessed and supported. This future is not about replacing universities with machines. It is about redesigning learning environments so they better reflect how knowledge is developed, applied, and evaluated in a real world. One major characteristic of the 2030 classroom will be AI personalized learning. Students will not all move through content at the same pace or in exactly the same way. Adaptive systems will help identify where each student is struggling or excelling and provide tailored pathways, practice, and feedback. This could be enormously valuable for student success. It could reduce the frustration of falling behind silently and increase opportunities for mastery. It could also make engineering education more inclusive by recognizing learner variability more effectively than rigid one-size-fits-all models. A second characteristic will be hybrid labs and global collaboration. Students will increasingly work across physical and virtual environments using simulations, digital twins, remote instruments, and collaborative platforms. Teams may span institutions, countries, and time zones. This more closely resembles modern engineering practice and opens exciting possibilities for internationalized project-based learning. A third characteristic will be continuous assessment, and this was talked about before. Rather than relying mainly on a few major exams, learning will be supported through ongoing feedback loops, smaller assessments, iterative assignments, and richer evidence of progress over time. This can make learning more developmental and less punitive. The 2030 classroom then is not defined primarily by location, it is defined by personalization, connectivity, and continuous learning. All of this leads naturally to a call to action. The transformation driven by AI is already underway. Institutions do not have the luxury of waiting for perfect clarity before they act. We need to begin redesigning curricula now. That means integrating AI concepts across disciplines, not isolating them in a few electives. It means embedding hands-on project-based learning with real-world tools and realistic applications. It also means rethinking review cycles. Traditional curriculum revision often moves too slowly for the pace of change we are facing. Institutions should consider more agile approaches, including pilot modules, rapid updates, interdisciplinary minors, or certificates, and experimentation with new course structures. We must also invest in faculty. No transformation will be sustainable if it depends only on a handful of early adapters. Faculty need development opportunities, incentives, infrastructure, and institutional support. This is not simply a matter of individual enthusiasm. It is a matter of institutional priority. And finally, we should actively engage with IEEE initiatives and the broader professional community. No institution should try to navigate this transformation in isolation. By leveraging frameworks, standards, resources, and collaborative networks, we can move more effectively and more responsibly. The institutions that act now will lead. Those that delay will find themselves trying to catch up in a landscape that will not slow down. Engaging with IEEE initiatives is a strategic opportunity to strengthen our programs and align with global best practices in engineering and artificial intelligence education. By leveraging established IEEE frameworks, standards, and educational resources, we can ensure that our curriculum remains current, relevant, and intentionally competitive. Active participation in initiatives such as IEEE Education Week, curriculum development efforts, and working groups allow us to stay at the forefront of innovation while contributing to the broader academic and professional community. And with that, I conclude my remarks here. I hope it was of value to you, and I pass it back to Professor Pears. Arnold?
Thank you, Babak. That was truly inspiring, and I think very insightful series of comments. I think we all agree that we have to lead the world here. IEEE is one of those major actors, but so are all higher education institutions in terms of preparing these future engineers. And it's very clear that we need to focus on engineering content and AI as a part of engineering content. And I think you make that point and made that point very well today. With that said, do we have any questions amongst our audience?
Yes, please.
Yep,
This is
absolutely, please.
this is Bhavani Shankar Chaudhary. I'm recently joined as a chair IEEE Education Society in Karachi section. I remained chair the Karachi section in the past, but now we have got very dynamic education society and taking a lot of interest. Everyone is taking a lot of interest. So our Higher Education Commission Pakistan, I remain member of Higher Education Commission from 2018 2022, and on the recommendation of IEEE, actually they started 3 hours credit hour AI course mandatory for all undergraduate and postgraduate degree programs starting fall 26. So that is great initiative they have taken to equip students across the disciplines with foundational AI knowledge, including ethics, applications to foster future ready workforce. And that's a mandatory AI course. All the curriculum, everything is designed. And I think 6,000 students already taken part in one of its another awareness competency tools program. So trying all our best at IEEE level education society in Pakistan, and hope with such a wonderful talk and all the support. We got, I think, about 10 participants from Pakistan, and one of my friend who recently joined IEEE on my recommendation, Dr. Ritu Raj Lamsal, he also joined from Nepal as well. So I think we'll take cue from here and do some more things with your support. Thank you very much.
Thank you.
Thank you.
I have a question, Mr. Chairman.
Please proceed, Robert.
Are there programs or textbooks that help teachers in high school and also faculty in university and in colleges about these good ideas which Babak just shared with us? Do these things
Thank,
exist?
thank you, Rob. Great question. Unfortunately, the pace of development is so fast that it has really outstripped the typical cycle of publication of textbooks that we are used to. Typically notice, with any, new area or new technical topic, there's journal articles and publications that eventually become the foundation body for an author or two to sit down and write a textbook, which could take months or a year or so before it gets published. Just take a look at how the first commercialized generative AI tool, ChatGPT, was 2 years ago, and that very same tool how it is today. Unfortunately, again, in line with what I mentioned in there, the AI tools themselves could be an excellent tool for training and sources other than textbooks need to be considered to be the sources of information, simply because by the time a textbook is published, I would argue that half of its contents are already obsolete because of the pace of change.
Thank you.
Yeah, I think we can agree on that. There are some resources available in my part of the world. I work at KTH in Sweden. Unfortunately, they're written in Swedish. So that makes them of limited relevance, I'm afraid. But there is some material that is being developed in Finland. So if you're interested, have a look at work that's being done in the K-12 space at the University of Eastern Finland. I'll put the text of that in the chat and you can follow it up. There's quite a big activity going on in Finland at the moment in terms of equipping students with AI competencies. It's also something that has just been adopted by the Swedish Schools Board. So the Swedish Department of School Education has introduced two new subjects, one AI with social focus or social implications of AI technologies and technical implications of AI technologies into the upper secondary school in years 11 and 12 of the Swedish high school system. So you could also look at the curricula of those courses, which are available in English as well as in Swedish. If you mail me, Rabab, I'll put my email address in the chat.
I think we've run out of time for any more questions. So,
yeah, well, thank you,
The
Professor Beheshti.
Chairman, can I have one question, quick question?
Very quick question. We'll go over time just for you.
Yeah, I am Ritu Lamsal from Nepal. In the context of generative AI and teaching learning process, especially in South Asia, it is very tough for the professors and academicians to really check out how the students are using this AI in their day-to-day work. So what do you suggest for the faculty members, how to motivate the students to ethically comply?
a great question, and unfortunately, I will have to give you a very, very short answer to that. So this is a problem that is endemic throughout the globe, and again, it goes back to my remarks that a shallow and unsupervised usage of the tools will simply result in diminishing fundamental understanding of engineering students. The traditional assessment methods are no longer valid now, right? So we cannot stop the students from using AI tools. So rather, creating assignments that assess the students' learning, knowing that they will be using these AI tools, and innovative assessment methods that really gauge their understanding of whys as opposed to hows will be essentially very critical now. So it is a problem which is inherent in the usage of the tool. We cannot stop it, but it simply means a complete rethinking of what assessment means, particularly in engineering education. Thank you for that question, but unfortunately, I will have to just stop here. We could talk a lot more about it.
So please join me in giving a round of applause to our speaker for a very, very good presentation. Thank you. Thank you very much indeed. I learned a lot today. I hope the other people who were here learned a lot as well. And we look forward to seeing all of you in our future events. And please, if you're not already a member, join the Education Society. This is the one-stop shop for all of your educational questions and needs. Please reach out to us. We look forward to engaging with you. Thanks again, everybody. Thanks for participating. Thank you, Babak.
Thank you. Thank you, everyone. Bye-bye. Thank you.